Hello. Today's session is the first part of a series on paper, just by for understanding some papers, some interesting papers. And today we are going to take a look at this paper called on majority, a fast majority voting algorithm. Fast majority voting algorithm. Okay. This is an interesting algorithm technique. So let's take a look here. So the paper itself has a section on the background of the algorithm, the algorithm itself, and some examples, and then even a Fortran implementation. The rest is more on the verification system used to provide a formal specification of the algorithm and then to provide a formal proof. So we will skip the formal proof part as it's not interesting to me, at least. I think the idea is, and the algorithm itself is what we want to take a look at. So the whole idea is trying to find a majority element in a multi-set of n votes or n elements. So you would have, for example, an array that has like A, say B, C, and here we can see that A is the majority element because it has the number of A's is bigger equal to than n divided by 2 elements of the array. So of course this can be implemented by just an obvious algorithm that scans the array or the votes. Let's consider each element of an array to be a vote a vote for one element. So for example, this is a vote for A, this is a vote for A, this is a vote for A, and this is a vote for B. Okay, so if an algorithm could be just to go through the votes in one pass, keeping a running like counter of the votes for each candidate encountered. So for example, having a counter here for A to be 3, and B it gets, we count 1, and for C we count 1. If the number of candidate is fixed, like we know the number of candidate in advance, then this algorithm can run in O of n. We'll just go through the entire array, keeping account for each. However, if the number of these candidates is not fixed, then both the storage and retrieval of the running tallies or running counters may lead to execution time that is worse than linear time. It may cause this algorithm to run even in O of n squared, because we will store them and then have to go through and compare again. So if the vote can be simply ordered, if these votes can be ordered, an algorithm with n execution time, like with order n, can be coded first to find first the median. So we can first use the median of. So if these elements, like say, so if the element of this array here, so if like the elements in A are ordered, then that means we can find the median. So we can just find the median using this algorithm called Rivest-Tarjan algorithm. Find the median, and then we can check whether the median has received more than half of the vote, and with that we can find it. So and this so the Rivest Sargent algorithm, let's just call it RT algorithm. It is known to have to do 5.43 minus 163 comparisons for n bigger than 32. So it is in a way linear kind of. Not really, because it has this big constant factor, but it has this very big constant factor 5.43. But the paper that we are taking a look at now can find the majority element in 2n comparisons using this majority algorithm that is described in this paper. So it's very useful. It doesn't even need the vote in the array or the stream or whatever to be ordered. It just needs them to be able to be compared by equality. So only equality is needed. So let's take a look at this algorithm using an example here of that is provided in the paper, which is suppose you have a convention center. So suppose we have a convention center. Okay, and suppose with delegates or voters, we have a set of voters. Okay, let's say V1, and each one of them is carrying a placard. Okay, each one of them has its placard. Let's call it C1, C2, and Cn. And these placards contain the candidate that they want to choose, so they contain the candidate name. And suppose in this convention center a floor fight ensues and delegates of each different persuasion begin to knock one another down. Like V1 choose candidate A and V2 choose candidate B, and when the fight happens, V1 knocks the candidate who choose B, which is V2, and V2 knocks the candidate who choose the opposite the voter who choose the opposite candidate, which is V1. And so it happens between each voters who have different candidates that they choose. So we suppose that each delegate or each voter who knocks down a member of the opposition is simultaneously knocked down by his opponent. So should any candidate field more delegates than all others combined, that candidate will win the floor fight, and when chaos finishes, the only delegates left standing would be from the majority of black. So if each opposite voter who chooses an opposite candidate knocks down the other, then the one that will be left means that it had more candidates than the others, because otherwise they would have knocked by the opposite voter who chose another candidate. So we know that what's left from the fight, if like VI is left after the fight, that means that VI is in the majority black, which means it has chosen a candidate who is in the majority if one exists. Okay, which means that VI or the candidate of VI is in the majority, or has the majority if there is one. I will explain later why do I say each time if there is a majority. Then is a potential majority, let's say. So why do I keep saying that if a majority exists? Because we may have, like, say V1 votes for A, V2 votes for B, V3. Say we have like only 5 voters. Okay. Say if V1 votes for A, V2 votes for A, and V3 votes for B, and V4 votes for B, and then V5 votes for like another one, C. So this one would knock this one would knock down this one, and each one of them would knock down the other, and we have left C. C is not a majority, but it's just the last one, and it has only one element after those have knocked down each other. So C will be left, but it's not as the majority element. But if this one, like, say, has chosen A, and we have here B, and we have here B, then this would knock this would knock this, and we would have A left, and A is the majority because it has 3 elements and the array size is 5, and so A would be the majority candidate, and that would be true. So if we have the information that there is a majority element, then the candidate that is left standing, or that is the majority element. So our conclusion here is, if someone remains standing at the end of such a fight that we are describing, the convention chairman, say there is a chairman that kind of is supervising this vote here, is obliged to count the number of, like, placards that have been, including those that have been down, to determine whether majority exists. So in our example here, we can just say C is the majority element, to go and count each vote. So if we go count, we can count A 1, 2, 3, or just 2, and B 1, 2, and C is just 1. So we can see that C is just 1, which is less than n divided by 2. So we can affirm that C is not the majority element. And in the case of B, if we go count, we can find that this is the number of A's is 3, and the number of B's is just 2, and we can know that A is the majority element. So the conclusion of this is, this algorithm here has 2 parts. The first part is where we pair off disagreeing delegates until all the remaining delegates agree, and this, let's call it the pairing phase. So this pairing phase can be done with just n comparison, and if pairing leaves any delegate standing, then those delegates that means that those delegates unanimously favor a single candidate, which, let's call him the nominee. So the outcome of this phase is having a nominee. And this nominee must be in the majority if a majority exists. The second part of this is called the counting phase, which is the phase that will allow us to know if there is a majority, so that we can confirm if the nominee that we got from the pairing phase is really the majority element or not. So the counting phase here just determines if the nominee received more than half of the vote. So it just checks if the nominee has like more than half of the vote, which is the size of the array divided by 2. So obviously this phase here requires just n comparisons. You are counting the occurrences of each one, so, and just one time, so we just just inspecting the array once. And so you can see that here also is probably n, and you can see that it's 2n comparisons, and we can kind of have the idea that this algorithm is over. So, but this paper is really is focusing on this phase here, cares more about this phase, the pairing phase. So let's say in this convention center example that we said, instead of them fighting each other, a simpler way could be just for the chairman to simulate the pairing phase by just visiting each delegate. So you would have, or each voter, V1, V2, Vn, and you would have the chairman here that goes and visits each one of them. So it goes and visits V1 first, and it keeps like in mind, let's say, both a candidate variable, so that it knows the current candidate, and a count k, which has the number of voters which shows this candidate. And its k starts off as 0, and when it visits, for example, V1, say for example V1 chose the candidate which is like, let's say we are starting at chose A, so candidate would be A, and k would be set to 1. And then after that, let's say the chairman visits V2, and it finds out that V2 has chosen candidate B. So what happens is that the chairman would put the, so the candidate was still A, so until the counter k is 0, and we visit one that wants another candidate, we keep the current candidate. So now when we find a voter that chooses a different candidate, we decrement k, so we set k to 0. And let's say we have V3 that chooses C. So in this case, k is equal to 0, so we change the candidate. So our new candidate becomes C, and we set k to 1. And you get the idea. If V4 has a candidate, chooses candidate C, then we increment k by 2. However, if V4 has chosen, let's say, A, then we decrement k by 1, so 0. And if the next one, which is V5, chooses another one, let's say A again, then k is 0, so we change the candidate to be A again, and we set k to 1. And when all the delegates here have been processed by the chairman, we know that the last canned value is in the majority if a majority exists. So let's look at the proof of why this works. So suppose we have n delegates. Or voters. So when the chairman visits the 8th delegate or voters, visits, let's say, the 8th voter, for, of course, I is between +1 and n. that means that the voters he has processed can be divided into two groups. So processed voters already by the chairman can be divided into two groups. One is K delegate in favor of cand, K voters. And another set of voters, let's say if he has processed it so far like L, that would be L minus K voters that can be paired in such a way that the voters disagree. So they can be paired so that they disagree with you. They disagree with you if we say U is the first group here. So from this invariant here, let's say, we can say that after processing all these voters, cand has a majority if there is a majority. So that's what we want to prove. So let's suppose there exists X. In order to prove that, let's suppose there exists X different from cand that has a majority, which basically is the contrary of our proof. Which means X has more than n divided by 2 votes. That means that X, because that means that X have received a vote from you, from the first group. X has votes but this is contradictory. That's contradictory with the fact that you has voted for cand. Because you has voted, they all voted for cand. So that means that cand is in the majority if a majority exists. So we prove it by contradiction. There is another proof in the paper by induction that is interesting if you want to take a look at. I'm going to skip it for now. So let's look at more example of this. So let's say we have 3 candidates. So let's say we have A, B, and C are candidates. Okay. And let's say we have them in this, we have votes for them in this order: C, C, B, C, 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 B, and C. And so our chairman here keeps the count by having both cand and the count K. Okay, so we start out in this A, And so we have the count now is A, and we increment K by 1. Then we move to this A here, and we find an A, so we increment this counter here to 2. Then we move to this one, to this A here, and we can increment our K here by 3. Then we move to this C, and now it's different than count, so that means we decrement K here, so K becomes 2, and our candidate changes to be the candidate doesn't change. Remember, we don't change candidate until K becomes 0, because it's still the majority. It still has 2 votes, and C still has had just 1. Until K becomes 0, then we have a new candidate that we can replace. And so we continue here. So now we are here, and we see is different than count, so we decrement K again. Now K is 1. So we go here, we have B. B is different than K, so we decrement the counter to be 0. And then we go to the next B in here. So, next B, which is here. So now K, this one, B is different than candidate, which is A, but K is 0, so that means we can replace the candidate. So what we do is replace this with B, and since we have a candidate, we increment K. So K becomes 1, and we move again to C, and C is different than B, so we decrement K, and we don't replace the candidate yet because K wasn't 0, so we just set K to 0, and for the next, we go to the next C here, and C is different than B, and K is 0, that means we can replace candidate to be C, and we increment K. Then after that, we go to the next here, which is C. C is the same as candidate, so that means we can increment K. And we go to the next again, we get to B. And so B is different than C, but K is 2, it's not 0, so that means we can just decrement K to be 1. We continue again, and now we are here in C, and C is equal to the candidate, so we can just increment K. And we'll go to the next, which is this C here, which is the same as candidate, that means we can just increment K again. So, sorry, I'm not sure, what was it? It was 2, so it becomes 3. And so we have our, if there is a majority, we can confirm that it's C. So we can confirm that C is majority if there is one only. Now, why we keep saying if there is one? Let me give you a counter example where we can find the candidate at the end of the algorithm, but it's not the majority. So let's do that in an example here. So let's say we have A, the candidates are A, B, and C. And we have the chairman here, which keeps the counters cand and K. And so we start off here in A, and so we have candidate A, K1, and then we go to the next one here, and so it's still A, but we increment this to be 2. And then we are here in the third one, so it's still a, we increment then k, and here we get to b. Yeah, let me just change this so that we get the right example. So let's say we have b and c instead. So when we get to b, we have, it's different than a, but k is not 0, so all we do is decrement k, and so we get 2 here. We continue, different than a, so we decrement k is not equal to 0, so we just decrement. We move again, we get to this here, it's different than a, and so all we do here is decrement k since it's not equal to 0, and now it becomes 0. So now if we go to c, we get c is different than cand, and k is 0, so we get to replace candidate with c, and we get to increment k by 1. And so you can see here that our algorithm says that c is the candidate for the majority element. But if you take a look, c happened only once, because these one, a and bb, cancelled each other out. So these cancelled each other out, and we were left with the final c. But c is not a majority. In this array, actually, there is no majority. And if we just rearrange this here to be like, say, a, b, say c, b, a, then we will probably find out that a is the majority candidate, although it's not. So this is why only if we know that there is a majority, then we can affirm that this is a majority element. So the implementation itself can be very straightforward. In the paper, it's done in Fortran, so it's a little bit hard to read. But the idea is just we go through the array, and we do the algorithm that we just did here. I will code it up later in Java and show you how it can be done. The rest of the paper is more on just formal specification and formal proof, so we can just like skip that for now, but I'll show the implementation in a second. Look at the algorithm implemented in Java, the one described in the paper. So this implementation here finds the majority element using the more algorithm that we just saw. And so this is just a check for like null and empty array, but what we want is this is the Chairman state that we talked about. So the Chairman keeps track of the current value and the current count. So we keep track of these both variables, and then we go through the array of values that we have here. So we check if the current value is 0, the current count is 0, which is this is the equivalent of k. Let's maybe rename it to k so that it's easier. And this is candidate. No, actually that's the inverse. So this is candidate and this is k. And so if k is equal to 0, then we put the new candidate, okay? And we set k to 1. If it's not equal to 0, then we can just check if the candidate is the same as the value is the same as the candidate we are keeping track of. Then we just increment k. Otherwise, if it's different, then we just decrement k. So this is the pairing phase, and at the end we would have the candidate that we need. And then in the counting phase, we just go through the array, and we count the number of occurrences of candidate that we got from the pairing phase. And we count the number of its occurrences. And we check if it's bigger than n divided by 2, the length of the array divided by 2. That means that it's a majority element, and we just return it. Otherwise, we just return null. That means there is no majority element that exists. And if we take a look at the example here that we have, and run it, we can see that here it should be 5. and we get 5. So as simple as that. I did it here for an array of int, but you get the idea. It can be implemented on all values that support equality, because that's the only thing that we are the only operation that we are doing here. So that's about it really. See you in the next session. Bye bye.